Hello. So here's the problem I want to talk about. Now, what does the problem says? It says that suppose that f is a function of real numbers and it's also a real valued function. What does this imply? It implies that f has its inputs from the set of real numbers like 2, 1 over 3, 4 over 5, 6, and the likes. So, and whenever it's acted upon, the result is also a real number. Okay, now suppose this function is continuous. What does it mean for a function to be continuous? The implication of continuity is that it implies three things. If a function is continuous, then the limit exists at a particular point. Then at this same point, the function must be defined. Then the third thing is that the limit of the function at the point and the value of the function at that point must be the same. That is what defines continuity at a given point. But what about over a region? Because here we will be using the fact that f is continuous over the set of real numbers. F is continuous over a region if for every value that we find in that region, f satisfies those three conditions that I mentioned earlier. That is, if you pick any point in that region, test the three conditions on them, it must satisfy it. So then you say that f is continuous over that region. But then it is not always the case for every function. Let me give us an example. For example, if you look at this function f of x equals to 1 over x minus 1, it is not true on the set of real numbers because when x equals to 1, this function will not be defined and hence one of those three fails. So that implies that f of x is not continuous for every real number. But this, unlike this first one, it is continuous for every real number that we have. Put any real number there, it will be defined. The limit will exist at that point and they will be equal. So you get the idea like that. So going back to our proof now, so I'll be proving, my proof will revolve around this. So I'll just lift this off to a blank page now. The product of f of a and f of b less than 0. So we have the product of f of a and f of b is less than 0. So what does this imply? This implies that f of a is either less than 0 and at the same time f of b is greater than 0, or f of a is greater than 0 and f of b is less than 0. So that implies that before you can produce the product of two values that will give a negative result, one of them has to be negative while the other will be positive. So we'll be taking these two cases into consideration. So let's see, for the first one, it says that f of a is less than 0. So if f of b is greater than 0, this implies that, so from inequality we know that we can flip this just like a mirror image such that 0 is less than f of b. This also implies this, because if 3 is greater than 2, then that implies that 2 is greater than 3. So if 3 is greater than 2, that implies that 2 is less than 3. So I meant that. So now if this is the case, then I can create a loop of inequality here such that f of a is less than 0. So I don't need to repeat that 0 is less than f of b again. I can just continue it from here. This implies that f of a is less than 0, less than f of b. So by intermediate value theorem, it says that if f is a continuous function over a given region, now we know that between a and b and on a and b itself, f is continuous from our definition. F is continuous over the set of real numbers. A and b are real numbers. So that implies that f is continuous at a, it is continuous at b, and for every value that is between a and b. So since f is continuous, so that's the first condition of the theorem. And the theorem says that, let us say that there exists a particular value between f of a and f of b, which we have here based on this inequality. So there's a 0 between this f of a and this f of b, and it says that there exists a particular element, there exists some k between a and b. This is an open interval of a, that is between, this means between a and b, such that f of that k equals 0. So before, we couldn't ascertain whether the real number, the element of the domain that gives this 0 is between a and b, but by intermediate value theorem we have been able to ascertain that this k actually is between a and b. Now let us take the second case into consideration as well. So we can have this such that f of b is less than 0. From this second condition, f of b is less than 0, and then since this is f of a greater than 0, you agree with me that f of a greater than 0, just like we did in the previous case, it also implies that 0 is less than f of a, and by so doing we can have this to be f of b less than 0, then less than f of a. So what does this also imply? By the intermediate value theorem, there will exist, so there exists as well, let's say this time around we are using a k1 that belongs to what? That belongs to a comma b. Now it does not matter, so because a is less than b, that is why it has to be between a and b, a first then b later, such that f of k1 is equal to what? 0. So we also use the intermediate value theorem here. So what do we do next is that, since we see that from the two inequalities, like from the two expressions that we have here, which means that it's either this is true or this is true. So if we decide to use one or the two of them, fine. So it must be true for one of them. That's the meaning of or. If it is true for this, then we are okay. So if f of k equals to 0, then just k is an arbitrary number which can represent anything. So I can replace my k with the c here. So concluding from this second one, that implies that there is indeed a c between a and b such that f of c equals 0. Like I said, k is arbitrary and then it does not matter. So since I'm choosing my k arbitrarily, then I can replace my k1 as c. So it's nothing. So this and this proves the theorem. Thank you.